Dear physics aspirants, right now I have the Kirchhoff's law and junction at the current leaving I1 and I2, and current entering is I3. The junction rule says I3 is equal to I1 and plus I2 at point H. Current entering is I2. There is only one current having H, and by junction rule that will also be I2 for those loops AHT CBA and AHTEFGA. The loop rules give here the formulae you will see here. Here is the photograph of Gustav Robert Kirchhoff, German physicist, professor at Heidelberg and Berlin, mainly known for his development of spectroscopy. He also made many important contributions to mathematical physics, among them his first and second rules for circuits. Gustav Robert Kirchhoff. Kirchhoff's rule: electric circuit generally consists of a number of resistors and cells interconnected in a complicated way. The formulae we have derived earlier for series, the parallel combinations of resistors, and not derived earlier for series or parallel combination of resistors, and are not always sufficient to determine all the currents and potential differences in the circuit. Two rules called Kirchhoff's rules are very useful for analysis of electric circuits. So when you study the electric circuits, Kirchhoff's rule will be required. Given a circuit, we start by labeling currents in each resistor by a symbol, say I, and the directed arrow to indicate that current I flows along the resistor in the direction indicated. If ultimately I is determined to be positive, the actual current in the resistor is in the direction of the arrow. If I turns out to be negative, the current actually flow in a direction opposite to the arrow. Similarly, for each source, i.e. cell or some other source of electrical power, the positive and negative electrodes are labeled as well as a directed arrow with symbol of the current flowing through the cell. This will tell us potential difference V is equal to P minus Vn, electromotive force IR. You will see. Here is the photograph, and here you will see also photograph example is, and here is another example, and equation for 3.57 between the positive terminal P and negative terminal N. Here is the current flowing and to P through cell. If while labeling the current I through the cell, one goes from P to N, then of course V is equal to electromotive force is plus IR. Having clarified labeling, we now state that rules of the junction rule at any junction at the sum of the currents entering the junction is equal to the sum of the currents having the junctions. Figure 3.22, and this applies equally well instead of the junction of the several lines. We consider point of a line. The proof of this rule follows from the fact that when currents are steady, there is no accumulation of charges at any junction at any point in the line. Thus the total current flowing, while is the rate of each charge flows into the junction must equal to the total current flowing out. Loop rule: the algebraic sum of the changes in potential around any closed loop involving resistors and cells to the loop is zero. This rule is also obvious since electric potential is dependent on the location of the point. Thus, starting with any point of if we come back to the same point, the total change must be zero. In a closed loop, we do come to the starting point, and hence the rule, it should not Noted that because of the symmetry of the network, the great power of Kirchhoff's rule has not been very apparent in example in 3.6. In a general box, there will be no such simplifications due to symmetry and only the application of the Kirchhoff's rule to junctions and closed loops, as many as the necessary to solve the knowns. In the network, can we handle the problems? This will be illustrated with the example 3.7. You will see here. With the help of this link, simplification for application of Kirchhoff's rules, the simulation for application of the Kirchhoff's rules for the simplification of the study, you will get this link for your understanding. We will meet in the next session with a lot more. Till then, thank you.